So we are talking about VSEPR theory, which is valence shell electron pair repulsion theory. Where we left off in the last video was looking at this molecule, which is H2O, which is water. Water has two bonded pairs, so pairs of electrons that are in a covalent bond, and then two pairs of electrons that aren't bonded to anything, and we're calling those lone pairs and bonded pairs. You can also see lone pairs sometimes described as unbonded pairs, but we'll be using lone pairs. So the idea of electron pair repulsion is that electrons are obviously negative, they all have a negative charge, and so imagine all these electrons with negative charges all around a nucleus. So when molecules are formed, so when covalent bonds are made, these all involve electrons being shared. So all the electrons all have negative charges, and so therefore they're all going to repel each other because they all have the same charge, which is negative, and so law of electrostatics states that like charges will repel each other. So these electrons are all pushing each other away, and so the shape that molecules end up with really depends on the type of electrons that they have, whether they're lone pairs or bonded pairs. And those electron pairs are going to push each other away as much as they can, so the repulsion is minimized, and yet the attraction between positive and negative, between the nuclei and the electrons, is maximized. So it's walking a fine line between minimizing repulsion and maximizing attraction. And the theory, remember, this is just a theory, it's very difficult to prove it, but a lot of the evidence that chemists have come up with does suggest that this is a pretty strong theory. The theory states that the interaction between different types of pairs of electrons varies. And so the lone pairs of electrons, those, if you have an interaction between two lone pairs, that's the strongest. And the reason is they're actually closer to the nuclei. So these two pairs of electrons from the oxygen are closer to the nuclei, which should be right in the middle, but you can't see it, than these bonded pairs. And so remember that each atom has, or most atoms have, a certain level of electronegativity. So oxygen's pulling electrons this way, but also hydrogen's pulling them a little bit this way. Obviously not as much because oxygen's more electronegative. So the electron pairs that would be here and here are actually slightly further away. So lone pairs and lone pairs, that's the strongest repulsion. Lone pairs and bonded pairs would be next, and then two bonded pairs would be the weakest amount of repulsion. So knowing that, how does that help explain certain molecular shapes or the shapes that molecules have? Well, to do that, we're going to go back to a different molecule. And that molecule is CH4, which is methane, natural gas. And so that's one carbon with four hydrogens around it. Carbon's in group 4, it makes 4 bonds, it's trying to fill its valence shell with electrons, and so it shares 1 electron with each of the hydrogens. So the shape that that will actually come up with is actually called a tetrahedral. And so this shape, the tetrahedral shape, I'm going to write that on there. Tetrahedral shape, it's the maximum amount of space that these pairs of electrons can get between each other, and still maintain that molecule. So rather than these pairs of electrons breaking off, for it to stay as one molecule, these have a certain angle, a certain amount of space between them, and that would actually be 109.5 degrees. So this is actually a representation of methane. You see that these angles are slightly bigger than 90 degrees. it'd be easy to fall into the trap of thinking, well, if there's 4 of them, if they all end up as north, south, east and west, then surely that would be the maximum amount of space they can get between them. But actually it ends up as being 109.5, which is more than 90. It's difficult to show, but this angle is bigger than 90. If I make it 90, or roughly 90, then that's less space between these 2 pairs of bonded electrons. So actually, more space, 109.5, is actually what happens rather than just 90 degrees. So, the maximum amount of space that these electrons can get between them, these pairs of electrons, can get between them is 109.5 degrees. So, it's a way to maximize the attraction, minimize the repulsion between the electrons, which all have the same charge. So then, you might start to see a trend, or maybe something similar in the water molecule. So if we had two bonds coming off here, and here, it'd actually look a little bit like a tetrahedral. It'd have 4 bonds, and they'd all be 109.5, but that's not the case because oxygen can't make that many bonds. But what it does have instead is 2 pairs of lone pairs, 2 pairs of bonded pairs. So rather than have an angle of 109.5, this angle is actually less, and the reason is you've got 2 pairs of lone pairs, and that's the strongest amount of repulsion between electron pairs. Then you've got lone pairs and bonded pairs here and here, and then bonded pairs and bonded pairs. So those are middle school children screaming during my lesson. Guys, stop screaming. Excuse me. So you've got 2 bonded pairs here, so the amount of repulsion is less than the lone pairs and lone pairs, and then even less than the lone pairs and bonded pairs. So imagine a negative charge pushing this way, so it's actually pushing this angle closer. So rather than have an angle of 109.5 between these 2, it's actually less. It's 104.5 degrees. And the reason is, and VSEPR theory, or VSEPR theory as it's sometimes called, the reason is because you've got different amounts of repulsion between different pairs of electrons. The reason for that is that certain pairs of electrons are actually closer to the nuclei. So these lone pairs of electrons closer to the oxygen than these 2, because these are being slightly pulled away by hydrogen. Even though it's not as electronegative, there is some pull this way. So, bond angle here between a tetrahedral, it's the maximum that you can get, maximum amount of angle between these bonded pairs. But then, these are all bonded pairs, so they all repel each other the exact same way, or with the exact same amount of repulsion. But then once you start to change a bonded pair for a lone pair, and in the case of H2O, you've got 2 lone pairs and 2 bonded pairs, so then that's going to have a big effect on the bond angle here. So the idea of VSEPR theory is looking at the number of bonded pairs and the number of lone pairs, and then trying to figure out how does that all arrange around a central molecule. And so I asked in the previous video, I asked the question, why did I draw these 2 hydrogens down here rather than have a bonded pair, a lone pair up here? Why didn't I do this? Well, the reason is this angle is actually less, puts less stress on the molecule, so it's actually easier for this molecule to form in this shape rather than this shape. So because you've got this lesser amount of repulsion between 2 bonded pairs. So that's why we draw H2O in this bent shape rather than this. Also, the other part of the story is looking at the properties that water has. It's actually, for a covalent molecule, it's actually got quite a high melting point, high boiling point as well. And it's because these lone pairs of electrons can actually redraw this. Remember that oxygen will be delta negative, hydrogen will be delta positive. So there's attraction between this water molecule and other water molecules. Because obviously if this oxygen atom is delta negative and these are delta positive, and that's going to be the same for every single molecule inside a sample of water. So there's going to be attraction between H2O molecules. Remember that the water can actually be poured down the string at almost 0 degrees because the water molecules stick to each other, and they also stick to something else like the string, or also the microscope slide. So water molecules are sticky. So some of the properties of water help the case that this forms rather than this. And also because of H2O being a highly polar molecule, this wouldn't be a polar molecule. Because remember that if you have two ends of the molecule that are identical, so a positive end and a positive end, that doesn't make it polar. So a lot of the properties of water help explain why this forms and why this doesn't form, and this forms. So in the next video, what I'm going to do is talk more about the shapes and how you figure out the shape of a molecule depending on the number of bonded pairs and the number of lone pairs.